Welcome, everyone. Our first PMEC seminar of 2026. I'm Judy Tweet. I run programs and communications for PMEC, or the Pacific Marine Energy Center. For those of you who are just getting acquainted with us, we're a research consortium sponsored by the Department of Energy on a mission to responsibly advance marine energy. We work across 3 partner universities: University of Washington, Oregon State University, and University of Alaska Fairbanks. This is the first of 3 seminars we're offering this quarter, all featuring deployments. You can find more information about upcoming seminars on our newsletter or LinkedIn page. Today's talk about the Turbine Lander is by Dr. Chris Bassett, and you may have read about the lander in the news this week. Chris is co-director of PMEC, also a research scientist at UW's Applied Physics Lab. He has over a decade of experience leading research in ocean acoustics, engineering, and marine energy. Take it away, Chris.
Will do. Thank you for the introduction, Judy. And let me get my slides up here and then we'll get moving. Can you please confirm my configuration here is correct?
Incorrect.
Incorrect. Always incorrect. All right. How about
Correct.
now?
That's
correct?
The one.
Okay, great. Hi, everyone. Thanks for coming today. For those of you who don't know me, I'm just going to apologize in advance. I prefer to walk around and be on my feet when I'm giving talk seminars, and I'm sitting today, so it might be a little rough around the edges, but here we go. As Judy mentioned, I'm talking about the Turbine Lander. I'll introduce what that is here soon, and I will specifically end on the topic of the next generation. And my goal is to provide some insights about the project from the beginning of the end. Before I jump right into my talk, I want to give everyone a few seconds to sort of step back to grad school, or maybe you are still in grad school, or before the time when you were an engineer. I know we have some engineers here in the audience, and think about being in the lab, performing some research, and coming up with what you believe is a great idea for a potential marine energy converter. And I'd like you to spend, say, just 15, 20 seconds here thinking about what the process of getting that idea from the lab into the field looks like. You could think about what might go wrong, what might go right, what tasks you need to do, anything, but just reflect on what comes to mind for you. And then we'll talk about the project after that. Go. Okay, so not a lot of time to think about what's a really big project, but I'm taking a few seconds here to take my own notes and think about sort of what occurs to me. And as we move through this, hopefully you can think about maybe what you got right, wrong, what that tells you about your experience in these sorts of projects. So I'm going to do this in sort of 3 chapters here, thinking about the road from this concept, taking that idea and getting into operations. The first chapter is going to be really short and takes us back to 2015. And that's with this concept of deploying a small-scale tidal turbine in situ. The second chapter ends in early, I guess it's probably winter, but in 2024, after the lander, shown here in the middle picture, had been operated in Sequim Bay for 141 days and is now very biofouled. And then the third chapter is really that next generation component, talking about what we did to take the lessons we learned from that first deployment and transition them to what we hope is a better performing system that we hope to deploy. I'm going to do this with more of some random stories and not get into a couple of technical details, because my goal here is to encourage especially some of the earlier career folks to sort of think outside the box, maybe not as much about marine energy and performance, but all the other things you need to learn and carry with you as you execute on these projects. So stepping back, chapter 1 is really all about this timeline. So around 2015, 2014, over a decade ago, Brian Pelagi's team, grad students, Ram Cavagnaro, Dom Forbush, Hannah Ross, Ben Strom, and probably others. I Sorry if I forgot that. We're basically in the lab working on cross-flow turbine hydrodynamics. And someone, I wasn't around for this, proposed the idea that of doing a proof of concept demonstration here. And this is really about the story of how that happened and what the timeline looks like and what surprises you see along the way. So this image here on the left is a newer picture, but just shows some of the a cross-flow turbine experiment in the lab. So we start with that concept roughly around 2015, and the subsequent 5 years are really spent developing that concept and some of the aspects of the design, performing a site assessment to figure out where the right place to go do that work is, and beginning to fabricate this stuff. By the time sort of mid-2020 rolls around, project's in decent shape. Most of the components are in place. Other components remain to be fabricated, but there hasn't been a lot of testing of the system. So that's going to come in the subsequent years. Around late 2021, we're in pretty good shape. We're ready to go to the field fairly quickly once we get our permits. Unfortunately, the rest of that timeline takes us a couple years down the road, and we finally get to put this in the water in 2023. So if you're a grad student now, and came up with a concept, you might be able to move more quickly than this, but I'd keep a timeline like this in mind. You're talking many years before you're reasonably going to execute on this for many, many reasons, and I hope to talk more about those now. So the Turbine Lander is this. This is the object, test article, whatever you'd like to call it, on the Seahorse, which we use to deploy the unit. So it's creatively called the Turbine Lander. Because it has a turbine centered here in the middle, this four-bladed cross-flow turbine, and it is on a gravity foundation or bottom lander. This unit is about 4 meters on each side, and its height is about 2.7 meters across, above the seabed. And basically, all of the components needed to run this system are packaged up in various housings right here. In the back left corner here, you see a white object with a bunch of parts on it. That's an environmental monitoring system I'm not going to talk about anymore today, but that was a big part of this project. What I'm going to say about this is about the operations, is very limited, but I will note that we operated the turbine when currents at the site exceeded 0.9 meter per second. And under those conditions, the speed at which the rotor spun was about 40 to 100 RPM. So that's just to provide you with a bit of context for the operational characteristics of this unit. So that's a very small amount of design details about this. We're going to get into some more as we proceed here. But I don't have time to get into everything. If you are interested in this, the design details, constraints, and efforts to characterize this unit are described in this paper that is open access. And in particular, if you're really interested in design stuff, the supplemental section, which is as long as the paper itself, really gets into the weeds on this. So if you find yourself looking for more, go find that later. Okay, so I skipped over a lot of the process here, and that's okay. We're going to dig back into that a bit later, but I want to talk about some of the unforeseen challenges that you might run into as you try to take a project to the field. Permitting was one particular challenge that we faced. I'd say more of a time constraint than a challenge, but our work began in earnest to get the permits to do this work in January 2017. Where basically the effort to deal with a biological assessment began. That was done with Cam Fisher at 48 North. That process basically played out, and we received a categorical exclusion, basically giving us most of what we need to deploy this device in September 2022. However, there was one remaining challenge on our hands, which was the Washington DNR required an aquatic lands easement. So we filed our paperwork to do that, and eventually we get that paperwork back in January 2023. Unfortunately, I cannot sign that document. That is above my pay grade. So our paperwork went into the capital projects office here at UW, where people wrangled over what to do with an aquatic lands easement, in an office where people normally spend their time thinking about acquiring land and building buildings. So there was a lot of emails back and forth about what this means and how this process works. Eventually, it gets signed. Everyone is ready to go, and that's in June 2023. But with such a long project timeline, so many times I had planned to put this in the water earlier, only to have a new barrier come up in its place. So I decided, nope, no more efforts to organize until I have all of the paperwork together. So that happens in June 2023. I start making my phone calls to vessels to get this in the water, and I can't find anyone to deploy until October 2023. But the good news is that's when we finally got around to doing it. So that was exciting. What about our plans to deploy? This was another area where the act of deploying the turbine through our project plans into a state of shuffling. We'll put it that way. So the RV Robertson is shown here on the left. Our initial plan was to deploy from this vessel, because this is our vessel here at the Applied Physics Lab and has pretty good capabilities. And in fact, if you read the paper, you will see many of the design constraints, the size, the weight, capabilities of the turbine were actually constrained by the A-frame capacity and back deck of this boat. So that was our plan. The goal was to take this vessel up to the site shown here on the right, which is the inlet to Sequim Bay, and basically 3 or 4 point more the vessel in the area, at which point we would set it down on the seabed. It's a relatively shallow site, so we could basically send some divers down to do some work, and this process would be relatively inexpensive. Unfortunately, a lot of the discussions around this happened before I became PI on this project. And when I went to organize this, there were a lot of reservations about it. For one, there's a partially exposed cable on the seabed that runs nearby. And if we were going to basically put the anchors, the ground tackle down to hold the vessel in place, that would put that cable at risk because we could not avoid crossing it. So that's not great. On top of that, there were some operational concerns, and our local operators basically said, hey, no dice, like we don't really want to do this. Can you go entertain some alternatives? So short answer to that is yeah, but I wasn't quite sure what to do next. Fortunately, people around here had some great ideas, and they recommended this particular vessel called Seahorse, which is a private vessel of a local marine construction company. And it's basically a much larger barge, about 108 feet long, and that is a giant 20-ton crane on it that can basically lift a large load at far bigger distances than we could ever need. One of the real compelling reasons to work with this boat is it's a spud barge, or other people might have heard of a jackup barge. So instead of anchoring, this vessel has some large spuds that it can drive into the seabed and basically hold station, and it can actually use those to maneuver quite close to the spot where we want to be. So this vessel's great, super capable for what it is, but it's quite expensive compared to our local oceanographic vessel. And then, of course, we need to work around their schedules. Either way, Northern Marine was fantastic, interested in doing this work, and so we decided to do so. So we had to make a plan, right? So we're going to send our device, our Turbine Lander, up to Sequim Bay. And how are we going to do it? We decide that the most appropriate way to do this is to build the Turbine Lander, fully fabricated here on the dock at our oceanography department, because there's lots of space. There's heavy equipment there. We have access to the power we need. And we can build that in advance. And then the vessel will leave its point of moorage, which is in Lake Union, right nearby UW's campus. And it's just going to steam a few minutes north to UW. And using its giant crane, it'll just pick it right off onto the deck. And from there, it can leave out from Seattle out into the Puget Sound region. And then based on the map on the right, drive up over to Sequim Bay there, and we can meet it. And that should all go nice and easy, no hiccups, right? Well, wrong. The reality looks a lot different than that. So the vessel itself while we were preparing for deployment and at the oceanography dock assembling this, less than a week in advance calls me and says, hey, we got a problem. Our vessel's too big to go in and out of the small lock. We have to go in and out of the large lock, and the Army Corps has announced a long-term closure to do maintenance. We are trapped out here basically for the winter with our thing because we are busy doing some work for the Navy and can't make it back before they're going to close. We need a new plan. They were like, can you just take it apart and drive it up? And I was like, no, that's going to be like a week of work. Plus, like, we've already tested the system or we're getting close. Like, that's not going to work. We don't have time for that. If we miss our window, we actually have a huge problem because we don't have another opportunity where the tides are suitable and there's not a holiday for over 6 weeks. So we're going to lose 6 weeks of our deployment if we can't find an answer to this. So we quickly figure out that instead of doing the plan, they can send over a small barge if I can contract with a local boom crane to come into the oceanography dock early in the morning, lift it onto the barge, transfer our equipment there. Then we'll take that and at 0800 or so, we'll go out of the small lock with the barge to load onto the other vessel. But the boat gets to the small lock after we do so, and the small lock is broken. And the pumps are not working. And so they can't get the vessel out. So it is dumping rain this morning. It's very cold. And this vessel has no interior. There's nowhere to hide from the rain. So the poor crew is just sitting on this vessel, getting poured on in cold weather for hours before finally they make it through the locks midday. They're able to perform that equipment transfer at sea and get the vessel up. As you can probably imagine, this is all very stressful, done on short order, and none of this is planned part of the budget. So just what happens when you do field work, maybe. Either way, we did successfully get our equipment up, and the following day we were able to deploy our equipment in Sequim Bay. So in the morning, we basically are all ready to go and we pull up anchor. Here on deck, I have the Turbine Lander ready for deployment. So we would come up with something maybe more complicated, but the water up there is actually quite shallow. It's only about 8 meters deep. So we can basically pick the Turbine Lander right off the deck with some slings and a load spreader. We can send it down to the seabed, and we want to secure the cable on the site anyway. So we want to send divers down. So we might as well just have them basically unshackle our equipment once we've tested it and we're comfortable with it on the seabed. So here, we're just preparing to put this in. We were in the interior of Sequim Bay in the morning, and this is the vessel basically just heading out to the site. That's PNNL's facility in the background. And we're just preparing to get this thing in the water and doing all the things that you do when you are ready for an operation. So now we are on site, and our job here is quite simple. We just want to set this thing down on the seabed. So it's all rigged to be picked up. But one of the things we wanted to do is that environmental monitoring package, which is shown on the very left side of the foundation here. We want that oriented perpendicular to the direction of the flow. So we basically sorted out to have another vessel come in with a large tagline and basically take some tension on that tag as we lower the vessel down to the seabed so that we can get that orientation of the platform right on the seabed. Pretty crude approach to it. It turns out it worked really well, at which point the cable, which is on deck here, is about a 160-meter cable, basically gets spooled out back to the facility and divers go down, secure it to the bed. All of our equipment remained comfortably in position following that for 141 days. So there you go. That's a pretty quick idea of deployment operations and some of the unsurprising things that happen. That's probably true. They are unsurprising, but unexpected. So here's one of the only looks of data, actual power generation data I'm going to provide from that, because I want to focus on lessons learned and what we did next. So the top figure here is current measurements for a good portion of that deployment period. And the y-axis is the inflow velocity at hub height. And so what we see is it basically is fluctuating down up and down several times on a daily basis and showing these broader temporal patterns associated with the spring neap cycles. Key here is that the peak velocities at the site are about 2 meters per second, a little bit higher at hub height. This bottom figure here just shows the power, electrical power generated by the turbine throughout the deployment period. Note that not all the powers are positive. A negative power means we're providing some power to the turbine to keep it moving. And this is actually happening quite often. The reason for that actually makes a lot of sense, I think, when you think about it. We'll talk about it in a minute, but we went through pretty extensive characterization of the turbine before we put it in. And at that point, we had realized some of the inefficiencies in the system that could be addressed with the second generation system. And we had a pretty good idea of how much better we thought a second gen system would operate at this point, but didn't have funds to build that. So instead, we chose to operate the system at the conditions we thought we could hit. And in addition, to just doing that, this would give us a huge amount of extra operating time and accumulate far more cycles, revolutions on our turbine, thereby stressing the system out more over time, so we could look at its survivability. There are two vertical red lines in these pictures. We're going to talk about this more, but these are associated with blade failures, and there are some lessons learned here. But the key takeaway on the bottom figure is when those blades failed, we actually still managed to keep generating power by being able to modify how we were controlling the system, and because it was fairly robust and survivable. So we consider that a pretty remarkable achievement, which I'll talk about more in a minute. Okay. So another quick prompt here. I'm going to give you a few seconds to think about this question. Our system underperformed in situ when it was deployed compared to control testing performed in advance. Can you come up with one or several reasons why you think that might have happened? Then we're going to talk through it. I'm going to give you 15 seconds. Okay, cool. Sorry, I know that's not that much time, but it's worth taking a second just to think what might not be going the way you expected. Because some of it was surprising to us. Biofouling was the first real big challenge we noticed, and we noticed it within 48 hours. So we had cameras and could view the system in real time. And we noticed very quickly that we were having several problems. The first was eelgrass was getting caught in the blades and basically the blade assembly. There were some small cracks in it, and those were basically large enough, even though they were less than an eighth an inch, for eelgrass to get caught in there and turn the blades into sort of like bearded objects floating around. That's not helpful. In addition to that, we actually had plenty of occasions where we had kelp get entirely wrapped around the turbine itself, as shown in this middle figure. And this figure out here on the right shows, I'm just going to call it a kelp forest. Either way, a huge amount of kelp drifting by in the background. So these examples where kelp got trapped around typically would come off within a tidal cycle, but these examples where eelgrass got stuck, it would stay there for quite a bit of time before it would come off. And so biofouling, you can imagine all that plant matter out there is really interfering with the hydrodynamics, creating extra drag and reducing the performance. So how do we determine that? What do we try to do to figure out what the impacts are? And lacking other good options, the approach we took was basically to find a period where the rotor is not fouled, and currents are basically zero, near slack tides, and we would step through a set of RPMs and measure how much power it took to drive the system when it wasn't biofouled. Then we would repeat it when there was fouling and make a comparison between the two just to say, what is the net difference in power requirements? And the short story there is that even in moderate cases of fouling, we are seeing that 50 to 200 watts, depending on operating condition, can be chewed up just by the presence of the plant on the rotor. That's not great when the sort of target average power output for our turbine is on the order of 100 watts. That's a real significant loss. So biofouling definitely interfered with us and motivated us to try to make some changes going forward. Another significant challenge we had, and this might be my most technical slide of this talk, is turbulence. So on the left here, we have what's basically a pretty typical measure for the performance of a rotor. So the y-axis is the coefficient of power, and it's y-axis coefficient of power, x-axis is the non-dimensional rotor speed. The coefficient of power is defined here on the right. It's just basically the mechanical power of your rotor in the numerator and the inflow power in the denominator, and this really represents your rotor's efficiency. One thing to notice about this particular curve is there's a peak right at about 2. And if I move significantly off that peak, my overall efficiency drops rather rapidly. And that should be a sign that a system that looks like this is going to struggle with performance if you can't keep it operating at the state you want it to be in. So what happens to us? Let's talk through this. So for my rotor, I don't have a specific CP curve, but instead I have some curves that represent the wire-to-water efficiency, or the total efficiency that combines that CP with the mechanical and electrical efficiencies of the rotor. And several examples of curves here are plotted here. The darker the color, the faster the inflow velocity. We see they have some similar structure to that curve that I presented on the last slide. And my question is, if I'm trying to maintain a constant control of the rotor, meaning it's moving at the same speed, what happens if my inflow velocity changes and I can't respond to it? It has great implications for our performance. So if my inflow speed increases, it might push me up to my next line here. So there's more power available because my inflow speed has increased. However, I'm moving off the peak of the efficiency curve, and the net impact of those two things might mean I make about the same amount of power, but I'm not going to generate much more, even though my inflow speed increased. That's okay. I can accept that. What I don't really want is the opposite, where if my inflow speed decreases, both I move down to another line on this, and in addition to that, I move out to the right side of the peak where my efficiency decreases overall. And as a result, I get hit twice when I do this. And this, it turns out, is the root of some of our challenges with turbulence. So when you are operating and trying to control a device, it's appropriate to figure out what time scale you need to use to control it. Tides themselves, if you think about them in an aggregate sort of average sense, if I do an average of on the order of 2 minutes, maybe 5 minutes, the mean currents aren't going to change a lot, but there are turbulent fluctuations of varying timescales in the middle. If I can track those perfectly, that would be ideal, but that's actually really hard to do. And if you can't do it well, you might always be chasing conditions that no longer reflect what the turbine is experiencing. And this is ultimately the problem we had. So this is 5 minutes of data. In this top plot shows three things. It's the velocity on the y-axis, and the red line shows a 2-minute moving average that's used to control the turbine. And the black and blue curves show 6-second averages. That's good enough to get a statistical sense of noise. That's pretty good, but still capture fluctuations in the inflow. And when we take those measurements and do that, what we actually see here is these wild fluctuations in the inflow that are happening on the scales of seconds or under a minute. So we are not fundamentally tracking those velocity fluctuations. And what this means is that this non-dimensional rotor speed, which is shown here in this plot, is optimized at about 1.9, which we hit okay with the upper part of the rotor, but for that lower part of the rotor in the inflow, it's varying wildly. And that means part of the turbine is just not operating that efficiently while we're out there. And the end result of that is we end up with these wildly varying inflow conditions that really drive variability in power production. So if there's less turbulence or we can track it, we can do well. But if we're just working off that mean flow speed and don't have a good way to account for that, we might struggle with power generation. And this points to a need to change things to do better control. Next challenge, mechanical losses. So before this system was actually deployed, we did some laboratory-based characterization to measure the assembly's friction. of all the components. How much is being lost when we just spin it in the laboratory? So that's what this plot shows. And really, most of our operating space is covered by 50 RPM to 100 RPM. So we're seeing losses associated with baseline friction on the order of 100 watts up to over 200 watts. That's not great. And those losses, the primary contributors to them are seals and basically the lubrication that we have in the bearing pack. So this is a problem we ultimately want to solve. I'll get to it in a minute. But another challenge we identified was a blade failure. I mentioned that earlier. So in this upper figure here, I'm not going to get into too many details, but what I want to point out is we have this complicated assembly where we have an aluminum strut that comes in and attaches to the blade, which has a titanium hinge, and there's a pin that holds those components together. And that pin is held in place by a fastener. So we had a blade failure. When we recovered the system, we didn't know what happened. So we wanted to do some forensic engineering. And the information we had available to us was we had been recording sound while we were out there, and we heard an impact. We know something in the case of both events hit our turbine and caused a lot of noise, but we don't know what precisely that was. When we dug through and looked at the blades that still existed and the ones that failed, we didn't see any telltale signs of fatigue. So that suggests something about the mode of failure. Next, when we recovered the system, we had two blades missing, and the bottom of both remaining struts, the fasteners that held the pins in place had more or less backed out. Not a great sign, because if those back out, we lose our pin retention mechanism. And the bottom struts that were intact on all of the different blades and had no significant damage to them, suggesting that the blades just came loose. However, the top strut had catastrophic failure, which I'll show on the next line, and damage to the anodization. So our story that we were able to pull together was that essentially, as shown here, the lower pin basically pops out of that hinge. When that happens, the blade is free to rotate up freely. Eventually, it spins over enough, and the titanium hinge makes contact with the strut and cams the pin right out of the retention mechanism, and you get a broken strut that catastrophically fails and looks something like this. So, interesting problem to have, something that we will keep in mind for our future designs. Okay, so I just spent a huge amount of time before I'm even at the next generation, but I think knowing what to do in your next generation, you have to understand what went well and what didn't the first time you went out. So our goals here are to increase power production. We have two ways of doing that. We can enhance our rotor performance, or we can basically mitigate our losses. We know we want to do something to fight against biofouling, especially the eelgrass that's getting stuck in the blades, which is something that's preventable. And we also want to increase its survivability. We don't want any more broken blades, right? So our approach is summarized pretty briefly in these coming slides. So first of all, we actually have 4 seals in this system. First, inside our generator housing, there's actually a seal on the generator. The reason is this generator is typically used on factory floors, so it has a dust seal to keep dust out. Do we really need that? The answer to that is no, we don't. And so we can get rid of that. We hadn't initially because it's a really expensive generator, and it's generally frowned upon to immediately void the warranty on really expensive equipment right after it falls into your hands. So we avoided doing that until we understood we had something good to work with here. On top of that, we have 3 seals located in the assembly that faces the water. Those are basically there to keep our lubrication in our bearing pack, and also to prevent the intrusion of sediment and seawater that can foul up our bearings. So those exterior seals aren't things we can do without, but we can remove that seal on our generator and our housing. And it turns out the act of simply doing that basically buys us back about 50 watts. So here are 2 lines showing the losses from operating the system with all of the seals installed, and then again once we just pulled out that dust seal. And as a function of speed, we see it increases a little bit. That's because your frictional losses will increase as your speed increases. But generally speaking, we're looking at 50+ watt offsets just by removing that seal from the generator housing. That is a huge gain from a relatively small task with relatively little risk. The second issue that we can try to mitigate losses on is our bearing pack. So the bearings basically are protected, sitting in this viscous layer of biodegradable oil. Much of the chamber that they're sitting in is quite narrow. At its narrowest is little as a millimeter or less. And because part of that's moving and part of it's not, there are viscous losses that are happening in there due to that shear. And so basically, we punched through some calculations for you fluids folks out there, basically treated this as a multi-chamber co-et flow and basically integrated our estimates for the power losses. And in the end, we figured out that we think that by just decreasing that viscosity, going to a lower grade oil, we could buy ourselves back another 10 watts or so under most of our operating conditions. So not nothing, but it's also not a lot. The risks associated with this are that our bearings are already sitting in a lubricant that has a lower viscosity than their specifications. We have decided that is a sacrifice we are willing to make to try to reduce our losses. And the lower viscosity oil could increase the potential for leakage or seawater and sediment getting in. But again, a risk we're willing to take for the reward of a bit more power. Another thing we did in this rebuild was look at our power electronics. So the initial system was really proof of concept. And one thing they did not want to invest heavily in up front was developing a custom power electronics solution for this system. And instead, off-the-shelf industrial automation power electronics with supporting tools were really used to drive the system. This stuff is fantastic for data acquisition, and it has a lot of flexibility like you might want on a factory floor. So it's a great fit for a proof of concept study. However, we realized that these were consuming a lot of power. They're relatively expensive and they're relatively big. So we wanted to be able to move away from them. And to do that, we actually collaborated with Embari, who built the Embari WEC, and their WEC has custom power electronics in it. And it turns out that our systems have remarkably similar needs, and we're able to adopt their power electronics with just changes to software required. There were almost no changes required to the hardware in order to integrate and work with that system. The benefits of doing this have been, instead of having two large housings, those housings that are shown in the images on the left, you could bathe an infant in them. They're big enough for that. They're not small. Instead of having two of those, we now have a power electronics package that fits within our generator housing. We've been able to lower the voltage, which means fewer losses when we're stepping up the voltage or boosting that power up after it comes out of the generator. The system is considerably less expensive, close to about 25% of the cost, although it would be interesting to see what we would get out of that in volume. Could be lower. It also has a much lower hotel load. So just keeping these power electronics going takes a lot less power than the old system, which is fantastic. And lastly, these are providing DC outputs that we can integrate with battery storage. So that's really exciting. The only thing is they're generally less capable. We can't acquire the same quality data and provide controls at the same sampling rate as our prior stuff, but it's still fantastic. Okay. Finally, a couple of things we did in terms of design was we said, hey, what can we do about the rotor design? We have two fundamental limitations we cannot violate. The first is the loads on our bearings, and we are sitting dangerously close to those under our design conditions, so we can't fix that. Furthermore, we can't increase our rotor size significantly because we're already pushing up against the overturning moment limits on our rotor. So maybe we can squeak about 10% in terms of a change in the size of our rotor out of this, but we can only do that if we change the aspect ratio. Ultimately, that's what we decided to do, but only after going through extensive design analysis to ensure that we weren't going to cause problems for our bearings and overturning moments. We also made changes to our specific rotor geometry, and I want to thank these 6 people right here: Aiden, Ari, Abby, Greg, Owen, Brian, and Aiden's paper, who provided invaluable feedback about how we might improve our rotor design. I honestly think this is the only part of our redesign that required a significant sort of scope that involved true marine energy expertise. The rest of the work was really driven by our ocean engineering, mechanical engineering, and electrical engineering staff. So we talked about all of the different things that we could change about our rotor, from the foil size to the preset pitch angle, constructions and assemblies. And in the end, we came up with a relatively small set of modifications, but a different aspect ratio for the turbine, slight increase in the core to radius ratio for the blades, and then redesigned the foils and basically did stress analyses to make sure the design was going to be good. And once we felt comfortable with all of that, we punched forward, found a new vendor, and built these composite foils. And don't have much to say about this other than we built a test article before committing to all this, brought this to the ME building, put on the Instron, and basically tested it up to 5 times the peak load that it will ever see. This is it with about 2 Honda Fits worth of mass pushing down on that rotor blade, which is deflecting almost 2 inches under that load of close to 6,000 pounds, actually. So system worked, came together at much higher than its anticipated or planned loads. So that was great. And the final design tests that we really went through were said, we want to streamline our system. We don't want any cracks in the assembly that can bring in biofouling. We don't want blunt components. We don't want exposed fasteners that are adding drag. And so the design ultimately looks like the system that we have on the right here, where we have a more streamlined system. There are no real ways for drag to catch onto this system. And this full system is being coated with an anti-fouling, non-toxic anti-fouling coating that was very successful in preventing barnacle colonization and macroalgae growth on the last Turbine Lander. So the efforts to design this are significant and involved a lot of detailed analyses to ensure that we were not going to design a system that would basically collapse under stress. So I don't have time to dig into it, but I do want to point into the complicated aspects of these assemblies for sort of people with a vision for marine energy. So this particular assembly looks like this. Every color in this represents a different material, and this is built up this way because of challenges with corrosion and mixed metal contact. So we use a titanium strut or shoulder on our blades here and a titanium pin because that represents the best sort of balance of strength and corrosion resistance that we can get behind. But we don't want to use titanium, generally speaking, because it's too expensive, or stainless steel everywhere because it's too heavy and difficult to machine. So we wanted to use aluminum struts. But if I have aluminum and titanium, those don't play well together. So we need to isolate all of these components from each other, which basically requires complex assemblies in order to mitigate that corrosion. So something that's really important when you think about your marine energy applications. In the end, how did we do? So our old turbine had performance curves that look something like this, where I have power on the y-axis and speed on the x-axis. And I'll just point out sort of the end conditions here. We're at about 2.25 meters per second. We saw about 1,500, less than that, watts of power generated. And we started generating power at about 1.25 meters per second. Our new rotor looks considerably better than that. So at the same inflow speed, we get over 1,700 watts of power generation. We start generating net power at about 0.9 meters per second, which is about where I believed we could land before we started the redesign process. We have shifted most of our conditions up by on the order of 150 watts, which is huge when you think about how that integrates over an entire deployment. And we've also helped reducing stall behavior, so we can move to more complex control algorithms that will help us break free of those speed challenges and turbulence issues that I talked about before. So we did great. We're going to redeploy this year. We hope you'll follow us and are excited to hear about it. And I'm going to close with a couple words of unsolicited advice to early career people here. And what I want to say is, if you want to stay in the space and work on field prototypes and everything like that, like, it's really important that you know your marine energy, right? Like, coming up with an idea that's going to perform in situ, definitely like 100% of that process is really dependent on your understanding of the hydrodynamics, the conditions, and things that you might be focused on a lot in your laboratory type research. However, when it comes to executing a field going project, your ability to navigate the marine energy space is actually a really small portion of what is required to get it done. It requires a huge amount of other expertise and being able to talk with other people who really are ocean engineers, who are experts in navigating the regulatory environment, maybe oceanographers. So my recommendations are to you are to recognize this complexity and approach these projects in a couple of ways. One, reading about other aspects of the industry and the space and getting to learn more about some of the things that may feel less relevant to your immediate marine energy research. It's tremendously helpful to be conversant in many other areas. Engineering, you want to be able to revisit derivations with engineers, talk about what it is that they're doing, communicate with operations people who understand how to get stuff in and out of the water, understand the environmental stressors and issues you need to navigate with these projects. And then finally, working on planning, logistics, record keeping budgets, and expanding your network of known vendors that you can trust to help make things work. That stuff can make or break a project in its timing at critical moments. And so learning how to do that and really investing your time and energy in that is critical to your future work. With that said, I want to acknowledge our sponsors, NAVFAC XWIC, that's the Navy, for their support for the turbine projects, and then some of these people, part of my large village that have helped make this happen. I won't say all of your names, nor is this everyone who contributed to this project. Thank you to all these people, and for most of them, I have put up the specific disciplines to give you an idea of what types of engineers have supported my work. So with that said, I want to go straight on to discussion. I'll stay after 2 hours if there's any need. I'm sorry I've gone, or after an hour if there's any need. I went a bit longer than I wanted. Here is reading that pretty much covers everything I talked about here in far more detail. This is all publicly available. So if you're interested in that, have at it. Questions, please.